Take a look around a typical modern operation theater. Behind these pristine walls sits a massive, highly engineered ecosystem. Hospitals invest millions of dollars into heavy-duty HVAC systems, ceiling-mounted HEPA filters, and complex medical gas lines to guarantee a perfectly controlled environment. But right before a facility opens to patients, during final airflow validation and pressure testing, the room fails. The alarms go off and the sterile conditions drop. The engineering teams scramble to check the ductwork and the filtration units, but the source of the pressure drop is often found right at the physical door frame. In critical care environments, a door is a primary infection control system. If it fails, the entire room fails with it. This diagram shows exactly how differential air pressure works. A sterile zone relies on positive pressure, meaning the air pressure inside the operating theater is kept higher than the space outside. This outward force actively pushes contaminated air into the corridor. Standard commercial doors ruin this physics equation. Without perfect alignment, the carefully calibrated positive pressure bleeds right out through microscopic leaks around the frame and floor. To make up for that tiny, continuous leak at the floor, the multi-million-dollar HVAC system has to work harder to maintain the room's pressure. Eventually, the system overcompensates, leading to massive airflow balancing failures. Fixing this requires a specialized healthcare-grade hermetic door, a barrier engineered to physically lock into the cleanroom walls and permanently seal the gap. The most sophisticated air filtration system in the world cannot maintain sterile conditions if the perimeter allows air to bleed out of the room. Air pressure is only half the battle. If you look closely at the machinery in a highly controlled laboratory or pharmaceutical cleanroom, you start to understand the extreme material standards required for the physical surfaces themselves. In commercial buildings, architects love decorative profiles, sharp grooves, and standard exposed metal hinges. In a hospital, those exact design features are active biological threats. Take a microscopic look at a standard door hinge or a textured groove. Over time, dust, pathogens, and microscopic particles naturally settle deep inside those sharp 90-degree corners. A proper operating theater door uses flush geometry and seamless edges. There are no exposed joints. When the cleaning staff sprays down the surface, it can be wiped completely clean in a single pass because the dirt traps have been entirely engineered out of existence. These doors also have to survive heavy, repetitive chemical disinfection protocols every single day. If the material isn't high-grade stainless steel or heavily coated galvanized metal, the strong cleaners will cause the surface to peel and crack. The moment a door surface cracks, it becomes impossible to fully sanitize. The barrier meant to protect the room turns into an active source of contamination. There is a widespread assumption that every modern hospital should be outfitted with futuristic automatic sliding doors, but automation has strict physical vulnerabilities. If the structural concrete is poured with even a slight unevenness, or if the site coordination between the flooring and the door track is off by a few millimeters, the sliding track degrades. Over thousands of high-speed opening and closing cycles, that tiny structural misalignment grind against the automation system, causing the hermetic seals to warp and fail. In high-traffic intensive care units, high-quality manual hermetic swing doors often provide more consistent reliability over long operational periods than complex automated systems. When you are engineering for life and death situations, consistent operational reliability has to take precedence over complex technology. If you trace the timeline of a standard hospital construction project, you usually see architectural layouts finalized early, followed closely by medical equipment coordination. The specific selection of the doors is almost always left for last. Delaying this decision until the finishing stage locks in fatal structural mistakes. By the time the door is ordered, the wall thicknesses are permanently set, and the uneven floor levels are already cemented in place. The financial consequences of this delay are severe. Within months of the hospital opening, the door frames start dragging against the floor, the internal rubber gaskets fail, and the delicate airflow logic of the entire ward collapses. Global authorities like the WHO emphasize functional performance over visual completion. For healthcare facilities, compliance is measured by how well the room retains pressure and resists contamination during actual surgical procedures. If a project team treats a highly engineered infection control system like a standard building material, they guarantee a cascading operational failure. Modern healthcare infrastructure is shifting its focus. Hospitals are moving away from cosmetic project delivery and evaluating their buildings based on strict, life-cycle-oriented performance. This requires integrated project execution. The cleanroom wall panels, the complex HVAC logic, and the customized doors have to be planned as a single, unified ecosystem from day one. This barrier determines if a surgical environment remains isolated from outside pathogens. When that heavy metal door swings shut and locks into its frame, it serves as the final, critical seal for the sterile zone. A modern hospital is a massive machine. Mastering its smallest, most frequently ignored engineering details is the only way to genuinely protect the patients inside.